Hey everyone, and welcome. Today we're tackling a Leetcode problem called Find the KTH character in String Game 2. It sounds a little complex, but we're going to break it down into simple, understandable steps. The key here is realizing that we can't actually build the final string, so we'll need a clever way to figure out the answer. Alright, let's look at the problem. We start with a simple string, just the letter A. We're given a list of operations. An operation of type 0 means we append the current string to itself. Basically, we double its length. An operation of type 1 means we change every character to the next letter in the alphabet, so A becomes B +, B becomes C +, and Z wraps around to A. After all these operations are done, our goal is to find the character at a specific position, which they call K. The trick is that K can be a massive number, so building the full string is out of the question. Let's walk through an example to get a feel for this. Say K is 5, and we have 3 append operations. We start with A. Our target index K is 5, which is way past the end of our current string. So we do the first operation. A becomes double A. The length is now 2. Still not big enough. We do the next operation. Double A becomes quadruple A. Length 4. Still not there. Finally, the third operation turns quadruple A into double A. Now the length is 8, and our index, 5, is valid. But what character is it? Well, let's think backwards. This big string was made by putting 2 copies of quadruple A together. Since 5 is greater than 4, the fifth character must have come from the second copy. It's equivalent to the 5 minus 4, first character of the original quadruple A string. Okay, so now we just need the first character of quadruple A. We repeat the process. Quadruple A came from double A plus double A. Our new target 1 is in the first half, so it's just the first character of double A. And that of course comes from the original A. So our final answer is A. This working backwards idea is key. This first approach, which the editorial calls iteration, formalizes the backward logic we just used. It's a two-step process. First, we do a forward pass. We go through the operations just to figure out how long the string will eventually become. We don't build it, we just calculate its length. We also count up any shift operations we encounter along the way. Then, we do a backward pass. We go through the operations in reverse. Every time we see a doubling operation, we ask, was our target index K in the first half, or the second half of the string at that point? If it was in the second, we subtract the first half's length from K to find its equivalent position in the earlier, shorter string. Every time we see a shift operation, we just undo it by decrementing a counter. After unwinding all the operations, we're left with the original character, A, and a count of how many net shifts were applied to it. Here's the code for that iterative approach. You can see the 2 loops clearly. The first while loop is our forward pass. It multiplies the length, L, by 2 for append operations, and adds to our answer counter ANS for shift operations. It stops once the length is big enough for coach. The second while loop is the backward pass. It divides the length by 2, and, if K is larger than the new, smaller length, it updates K'. If the operation was a shift, it subtracts from our ANS counter, effectively undoing it. Finally, we return the character as shifted by whatever our final ANS value is, using a modulo 26 to handle wrapping around the alphabet. Now for the second approach, which is a really elegant mathematical solution. It uses a fantastic insight about binary numbers. Think about it. Every time we do a doubling operation, we're essentially making a decision. Is our target character in the first half or the second half? This is a binary choice, a yes or no question. It turns out, the binary representation of our index K-1 holds the answers to all these questions. If the binary represents bit in the binary form of K-1 is a 1, it means that at the binary represents doubling step, our character was in the newly added second half. And these are the only steps that matter for type 1 shift operations. We only accumulate a shift if we cross the boundary into the new copy. And here is the code for the mathematical approach. It's much shorter. We initialize our shift count, ANS, to 0. Then we loop from the most significant bit of K-1 down to the least significant. Inside the loop, we use a bitwise AND operation to check if the I-GOS-TH bit is a 1. If it is, it means the I-CHEAN-BTH operation is one of the critical steps that defines our character's final state. So we add the value of that operation, which is 1 for a shift, and 0 otherwise, to our ANS counter. After checking all the relevant bits, we just calculate the final character, same as before. It's a very direct and efficient way to get the answer. So how do these two approaches compare in performance? Amazingly, they're both very fast. The time complexity is big O of log k. This is because in both methods, the number of loops we run depends on the number of bits in k, which grows much slower than k itself. Doubling k only adds one more bit and one more step to our loop. For space complexity, both are big O of 1, or constant space. We only need a few variables to store things like the length and our answer counter. The memory usage doesn't grow no matter how large k gets. So let's wrap up with the key takeaways. First, when you see a problem where something grows exponentially, like our string doubling in length, a great strategy is to think about working backwards from the final state, instead of simulating forwards. Second, never underestimate the power of binary. The binary representation of an index can often encode the entire history of choices in a process that involves repeated halving or doubling. And finally, always pay attention to the constraints. A huge value for something like k is a massive hint from the problem setter that you should not try to build the object directly. Look for a smarter, more abstract way to find the answer. And that's a wrap on this problem. I hope that explanation helped clear things up. If you found this useful, please hit that like button, and consider subscribing for more Leetcode breakdowns. If you have any questions or a different way of solving it, drop a comment below. And hey, if you're feeling extra supportive, the Boba Fund is always appreciated. Thanks for watching, keep up the great work, and I'll see you in the next one.